All right, we're going to go ahead and introduce our next speaker. So we have Gwendolyn Flaherty, and she's going to talk about a construction of set theoretic solutions to the Yang-Baxter equation.
All right, hello everyone. Thank you so much for coming out here. And I also want to give a thank you to the organizers of NCUWM for putting on this amazing conference. Now, before we get into the construction of these solutions, let's take a look at what a set theoretic solution on the Yang-Baxter equation actually looks like. So it consists of two components, a set B and a function R on B cross B that satisfy this equation here. And to clear up a bit of the notation, everything that looks like a cross product here is actually an individual function. And so this is a composition of three functions. And wherever you see ID, that stands for the identity map on B. So here's the way that a function of this form works. We see that R takes two elements because it takes inputs from B cross B. So for an element of B cubed, or B to the third power, if R comes first, it acts on the first two elements, A and B, and the identity will leave C fixed. If the identity comes first, it will act on the first factor A, and R will leave B and C fixed. So here's an example of a set theoretic solution. If we have any set B, we can use the function R that switches the ordering of an element AB, and we can see that these two, this set and this function, form one of these solutions. If we focus on the left-hand side of the equation here, we can see that R switches the order of A and B, the identity leaves C fixed. The identity then leaves B fixed while R switches A and C. And then finally, R acts on B and C, and the identity leaves A fixed. And even though we have two different function compositions that we start with up here, we get the same result, and that's why this B and this choice of R form a solution. Now, these solutions are very important in many realms of both math and physics, statistical mechanics, quantum physics, knot theory, to name just a few. So my research goal was to identify as many of these solutions as we could. And a tool that we can use to do this is something called an idempotent matrix. So we're going to denote idempotent matrices with the capital letter E. And they are square matrices such that their squares equal to themselves. So as an example, here is an idempotent matrix. If we can square it, we see that E is equal to E squared, so this is an idempotent. Now, for this method of construction, we're going to be using B of the form an elementary finite abelian P group, which is just a fancy way of saying a group of the form ZP to the nth power. Where P is prime. And we choose our idempotent matrix E to be in this ring of the form MNCP, where N is the n by n matrices, and they have elements in CP. And by extension, we can also construct, we can also use B, that is a choice of cross products of these elementary finite abelian B groups. So if you want to have a lot of fun, you can take three of these, I've color coded here, three different elementary finite abelian B groups, or pack as many as you want, and their cross product will also serve as a B. And in this method of construction, we'll treat elements of B as vectors, and define our function R with our idempotent matrix like this. Here, I stands for the identity matrix, and A and B are our elements of big B. And if you look here, we can see that R is a solution to the Yang-Baxter equation through this algebra here, which you don't have to read all of. But a cool thing to notice is that the idempotency of E is very conducive to both of these sides becoming equivalent in the end. Here, for example, we have E minus E squared, which, because E is equal to E squared, will just zero out this term. So there are a lot of instances of that and ways that idempotent behavior can actually form the solution. So here's a couple examples of simple choices of E. Let's let E be the zero matrix. If we plug that into our formula for R, we just get the very first R that we use to construct a solution, the one that switches the ordering of A and B. Pretty cool, right? And if we use the identity matrix, we plug it in and we get R of A and B is just equal to 0 and B plus A. That's another solution. For a more complicated example, we could let E be this 3 by 3 idempotent matrix here. Trust me, it is. And B is the group Z5 to the third power. And we'll take two elements of A and B in our big B and write them as vectors like this. We plug them all into our equation for R, and this is our solution. So it's really cool. We can take an idempotent matrix and construct kind of a complicated looking solution that we might not have been able to get without the use of the idempotent matrix. So we want to identify as many of these idempotents as we can. One of the first ways we can look at this is by noting that idempotency is invariant under similarity. So A is similar to a matrix D if A is equal to D conjugated by some other matrix C. And conjugation is just where, if you're conjugating by C, you multiply by C on one side and C inverse on the other side. So A and D are similar. And we can see that if A is an idempotent matrix and similar to D, D must also be idempotent. This is cool because if we can find some idempotent matrix that when you conjugate it, it generates this massive group of other matrices, all of those other matrices will also be idempotent. And a good matrix that we can use to do this is something called a Jordan canonical matrix. So this is kind of similar to the idea of fractions, how fractions can simplify into a simplest component. Like if you have 4/8, 3/6, 2/4, those all simplify to 1/2. And you can kind of multiply that by some constant to generate this family of fractions. This is sort of a similar thing. All square matrices have this base idempotent, or this base Jordan canonical matrix. And so but instead of multiplying by an integer, it's conjugation. And Jordan canonical form of a certain square matrix M is of this form. The diagonal entries are M's eigenvalues. A diagonal entry appears as many times as its multiplicity in M's characteristic polynomial. Elements on the superdiagonal, which is just the elements directly above the matrix diagonal, are either 0 or 1. And all other elements are 0. So as an example, if M is the matrix 2, 1, 3, 4, its eigenvalues, which aren't immediately apparent, are 1 and 5. And the Jordan canonical form of M is this right here. And because it's its Jordan canonical form, we know that M and J are similar. So if we can find idempotent Jordan canonical matrices and conjugate them, we can produce a whole similarity class of idempotent matrices to use to construct our Yang-Baxter solutions. That's not convoluted at all, right? So let's take a look at what idempotent Jordan canonical matrices actually look like. They are diagonal matrices, and they contain elements of either 0 or 1. This is something that I determined in our research. And two idempotent Jordan canonicals are similar if they contain the same number of ones on their diagonal. And we really only care up to similarity because two similar Jordan canonicals will produce the same similarity class. So up to similarity in a given ring of the form M and ZP, there are n+1 idempotent Jordan canonicals. We denote them JK, where K is the number of ones on their diagonals. And here's the set of idempotent Jordan canonicals in M3ZP. So here's an example of generating a matrix with one of these Jordan canonicals. If we choose our Jordan canonical matrix to be J1, our set that we're deriving it from to be M2ZP, and we conjugate it by this matrix right here. We're just choosing any invertible matrix. This is our choice. And we get this right here. This might look familiar because it's the very first idempotent matrix that you saw. This is how I found that. So now I would like to show you how I counted the amount of idempotent matrices in the ring M2 with entries in ZP. But before I do that, we need to account for redundant results occurring. Thankfully, because different Jordan canonical matrices represent different similarity classes, two Jordan canonical matrices can't produce the same E when they're conjugated. But if you have the same Jordan canonical matrix JK, and you have two different invertible matrices, C and D, they could conjugate JK to produce the same matrix. Here's an example of this here. C is different from D, but when we conjugate J1, the same idempotent is created. So So taking that into account, let's count the idempotent matrices in M2ZP. First, we note that J0 and J2 are just the zero matrix and the identity matrix in this ring respectively, and they always produce themselves when conjugated. So they only produce one idempotent each. And now we'll look at J1, which is the more interesting case. So we can recall that redundant E are generated for some C not equal to D. These two sides are equal to each other. We could rewrite this equation by conjugating both sides by C inverse. And that produces J1 is equal to this. And we could rewrite C inverse D here as submatrix A. So this actually kind of simplifies to J1 being equal to J1 conjugated by submatrix A. So for any instance of these problem C's and D's, we could just, there are as many A that exist such that this is true. So if we count all of those A, we can weed out all of the instances of duplicates. And I found that this is the case that that A conjugates J1 to produce J1, if and only if A is diagonal. So the size of our general linear group, which is where we get all these invertible matrices that we can conjugate J1 with from, this is the size of it right here. And there are p-1 squared diagonal matrices in this general linear group because if either one of the diagonal entries were 0, it would be a singular matrix and would be in the general linear group. So there's p-1 squared, p-1 choices for each diagonal entry. So if we divide out the amount of diagonal matrices from the total order of this group, we get p squared plus 1 idempotent matrices that are generated by J1. And adding back in our J0 and J2, we have p squared plus p plus 2 idempotent matrices total in the ring M2ZP. So that's what I found so far. In the future, I'd like to generalize this for any ring of the form MNZP. I want to expand to constructing solutions with B of any finite abelian group, not just an elementary P group. An example of this would be something of the form of a prime power, like Z mod P to the K. And I also think it would be cool to look at solutions where B is a new type of set entirely, like a dihedral or symmetric group. Does anyone have any questions?
Questions? I was going to ask, first of all, this is really cool. How much did you use kind of eigenvalues to get general, just kind of a starting point? Does it kind of seem like that would be easy to use for the similar matrices?
Yeah, thank you. So if I go back on the slides here. Eigenvalues were a key part in actually proving that idempotent Jordan canonicals have this form where they're diagonal and they have either 0 or 1 on their diagonal, because 0 and 1 are the only eigenvalues that when squared equal themselves. And that's kind of a part of the proof that when you square one of these, the matrix multiplication works out that these eigenvalues have to be idempotent themselves for the entire matrix to be idempotent.
Are there any other questions?
All right, thank you again for coming out. And I'd also like to give a shout out to my advisor, Dr. Alan Koch. He's been amazing in helping me do this research. He's really awesome, and I feel bad for not putting a thank you in